Good morning. Yeah. So I'm just trying to say, it's good that it's only myself in Zoom. Probably too early for everyone. And yeah. Anyway, I'll start with what's the program for this week. Like after this lecture, then on Friday 2 to 3 I'll run some sort of some calculations which I would like to show you, and then after that from 3 to 4 the tutorial will run, and then there are no labs in this week, but I will upload some material for the PSCAD lab this week. Okay, so you can get ready for that, and then you know what activities needed to be done. But as I said before, the due date is quite far. Okay, but because that according to the current guidelines we can't give you multiple assessments in one course, right? So there are only 4, has to be 4 assessments, and then there are some regulations. Okay. Anyway, so someone joins. No, I'm not sure whether the people are joining through different line. I think this should be the one. So what I will do then, give me 1 second just to double check. I will check the do you have any laptop? Can you please join one of the Zoom sessions, and then to see whether I'm in the same session, just to double check. Can you click on the link that is given on the course learning site?
I'm in, but I don't see.
Pardon?
I'm in, but I don't see.
Oh, okay. Which means that probably. Can you tell me the what is that? Okay.
I go to the one in learning resource.
Yeah. Are you there now?
I am there right now.
Yeah. So can you give me the meeting ID? You can check it at the top left-hand corner. 81 833 175 76090. Right?
Yeah.
Oh yeah. Everybody's there. Okay guys, sorry for the delay. I was in a different Zoom session. Can you guys hear me? Yep, thanks Richard. I will now share the slides. Okay, so hope you can see the slides as well. Yep. Okay, thanks. What we discussed so far, and today morning I mentioned that the plan for this week is that after this 2-hour lecture, then there will be another 2-hour session on Friday. In the first hour, I will take that and then do some calculations related to the things we discussed today, and then the tutorial will run in the next 1 hour. Also that I will upload material required for next week, especially for the PSCAD. Those sessions are starting next week. I will post some material including videos this week. So far what we discussed was that basically some sort of an introduction to the protection, and then why protection is required, and then I discussed a little bit about what is a substation, right? And then the components associated with the substation is quite important, like transformers, bus bars, and then switch gears. And there are a lot of components associated with the substation environment. And then some of these equipment are used for the protection systems, and then some of the equipments are protected by the protection systems, like bus bars and transformers. So we will discuss all these schemes in coming weeks. And also that I mentioned about the typical protection scheme, like you have control and communication part, and then measurements and operation sections, right? All these things that I discussed in the last class as an just to give an overall view of protection scheme. And also I mentioned about this specifically this IEC 61850. There will be a lecture on this from one of the industries. If he's from Omicron, and then he agreed, and then if he couldn't, because the office is in Melbourne, if he can't, they couldn't find a way to travel here, then we will offer it as sort of a recorded or online lecture. But there will be one section on IEC 61850, which is basically some sort of a guideline for industries to how one needs to automate a substation, right? And then they are mainly focused on the communication, and then how to communicate between different units. And also I discuss about a little bit about modern substation, let's say distribution system and a traditional distribution system. In a traditional system, that you will see that it is a radial unidirectional power flow going from the generators to the load. But in a modern substation, if you look at it very carefully, you will have a lot of distributed generation components. Like it could be solar PV, it could be local generators, it could be batteries, right? Number of different ways of feeding power into the grid. And therefore, that affect the protection schemes. So the traditional systems, when you are looking at only one direction, in a modern system, sometimes you may have to look at both directions, and then you may have to understand that reverse power flow is allowed, because in the let's say traditional systems, that reverse power flow is not allowed. So you may have to do a lot of these modifications or setting modifications in a relay. You don't have to replace the whole hardware, but you may have to change the settings. As I said, we will discuss a little bit more in detail in I think latter part of the course about distributed generation, and then what sort of protection schemes associated with that. But keep in mind that in the distribution protection scheme, that you may have generators like connected to the feeder, but the feeder is traditionally connected or feed through these sort of transformers, right? So the power, this is the utility feeder. It comes through this transformer and then going into these loads. But now the difference is that now the power is not coming through this feeder, but sometimes it could go from these generators to these loads. So that you need some sort of a protection schemes for these generators, as well as you may have to change even sometimes hardware. If, let's say, oh, am I not? Sorry. I think I'm using the mouse on the other computer, so you can't see it. So the generators here need some sort of protection schemes, as well as sometimes these local loads, we call it as the short circuit current. What happens, or what will be the magnitude of the current if there is a short circuit around this area? That current will increase if you have these generators. Therefore, sometimes that you have your circuit breaker capacity has to be increased, right? So those sort of things we will discuss in the latter part of the course. So I discussed a little bit about the benefits of a protection scheme as well. The number one is the personal safety, and then the security of the assets, and also the if you are looking at revenue, you want to minimize the loss of revenue as well. So that's why that you need, like as an example, if you can, for a certain fault, if you can isolate only 10 customers instead of 100, then you can still feed 90 customers. So that's something related to the revenue of supply and the reliability. So the system reliability is also quite important. And also the quality of supply, because nowadays we all use number of computers and then sort of electronic devices, and then they interfere with harmonics and probably over voltages or under voltages, they respond in different ways. So that we want to maintain that good voltage profile. For that, sometimes you need protection schemes to avoid or disconnect some loads or sources which produce these sort of unnecessary harmonics. And the other thing is the reducing the impact of the new modern loads and generators. And that's what I mentioned just now. And what else? Yeah, distribution network reliability, because if you think about in Australian context, bushfire is quite important. Like if you think about a couple of years back in Victoria, there was a big issue with the bushfire, which is initiated by these electrical transmission lines. And then one of the issues with this, the protection schemes for typical distribution feeders is that when there is we call it as high impedance faults, or when the fault current is very, very small, right? Usually when there's a fault, current is large, right? But when the fault current is small, sometimes the system can't recognize it. But still, that small current could create some sort of a temperature increase in surrounding area. And then that starts like when, especially when the, let's say, vegetation is very dry, right? That could start some sparks or sometimes lead to a big bushfire. So that people have already developed some mechanisms to identify that sort of high impedance faults and and then disconnect the lines in that sort of situations. Yeah, so when you are looking at these sort of protection schemes, like it's sometimes affect your personal life as well. Like as an example, if you can't watch your TV because your neighbor is putting a PV into the system, then you're not happy, right? So that everyone like you have customers whose requirement are different. One wants to use some sort of electronic device, another probably has to use a pool pump, right? So that, but those devices should have minimum impact on the grid. So that's something sometimes looked after by the protection schemes as well. Okay, so within the course you will learn all these sort of different protection schemes, starting from overcurrent protection, which is the most common ones, and also that we will discuss things called directional overcurrent, impedance relays, and also differential protection, and then we will go into pilot relays, right? So a lot of different mechanisms that are used in the protection systems. Then we will look at the characteristics of different relays, like how do you identify or distinguish a fault from a normal operating conditions. That is done through the relay characteristics. And also that we will look at not only just the characteristic and then the theoretical calculations, but also we will look at a little bit about the construction of relays and then circuit breakers, what are the other components associated with schemes. And finally, we will look at some current trends like distributed generation schemes and things like that, and what different countries, how they implement different protection schemes depending on their grid codes. If you look at this past and future, the current, you can clearly see that this was still, these sort of relays are used in some of the old substations. They are reliable, right? They are mechanical. Nowadays, they are just computers, right? So what you have in the lab is the one in the right-hand side. I have one in my office, one of these. Probably I'll bring it next time. So it's the old one is if you look at it, then it's easier to understand the terminology with the old one. Because some of these protection scheme terminology, they are used for these old ones. And then what they have done is they implement those conditions in a digital relay, right? So that's a software code, right? So you write a software to identify the same conditions. But here, everything happens mechanically, right? So those are the major changes, and then the digital ones probably more accurate, but then still some of the old ones are still, after 50 years, is still working. Because if you think about a relay is not there to operate all the time, right? So the relay will operate only when there are certain faults or unnecessary conditions in the system, which the system is designed not to happen, right? So that the relays basically are not, since they are not operating all the time, that the reliability still goes on, and then they are still working fine. Okay. So when we are looking at these sort of protection schemes, the main component one could think about is the relay. When we are thinking about the protection schemes, relay, because that is the brain of the protection scheme, right? Brain means the processing, right? It processes information. So once you feed some information to your brain processes and then takes some action. So that is what the relay does. Relay will take some information from other components, and then it will decide what action needs to be done, and then send that signal to somewhere else. So that is very similar to the processing of our brain. So now, to process some things, you need information. So who provides that information? Information is provided by instrument transformers, right? So that instrument transformers like sensors, our eyes, ears, right? So you capture the information and then feed it to the relay. So that is the second step of it, right? So that you need the brain, because to do some actions and then take any, let's say, decisions, then you need a sort of a processor. And then to process, you need information. To get that information, you need some sort of a device which measures voltage and current, because we are not going to measure anything else, right? We are going to measure mainly the voltage and current. And the instrument transformers are the devices what we use as sensors, right? So when I say instrument transformers, we know that transformer is a device which increase or decrease the voltage level or currents. So in instrument transformers, we are going into detail of these things later, but instrument transformers, remember, we have two types, current transformers and voltage transformers. For the protection schemes, two types, CTs and VTs. CTs means current transformer, probably in the line, the current is 1500 amps, but your measurement side, the relay cannot take that sort of high magnitude of currents. Then definitely the relay will be damaged. To avoid that, you reduce the current magnitudes to a level of, let's say, a couple of amps. And that current is measured by the relays and then take appropriate actions. And the same concept applies for voltage. So voltage is dropped from, let's say, 220 kV to 120 volts. And that 120 volts can be measured using a normal measuring device. So that helps to, for two things actually, for CTs and VTs. One is bring the measuring quantities into a safer limits, so that you are measuring them in the safe limits. The second thing is that then if you think about the transformer construction concept, your main circuit is now isolated from the secondary circuit. There is no electrical connection, because in a transformer you have separated windings, so that the primary side voltages or currents will never appear in the secondary side, right? So that helps to isolate those two systems, and then that helps to avoid, let's say, or safe operation, to set the safe operations. Otherwise, higher voltages would appear in the measuring sites. So those are the main advantages. These are some photos of a CT, current transformer. Okay, the right-hand figure, which is a, if you go into a substation, it is you will see these sort of big devices, right? Why? How? Like you will see number of these sort of columns in a substation. How do you identify whether it is a current transformer or not? What is the easiest way? What do you think? There are other devices which are also mounting on poles. It is the way the wires are coming in and going out, right? If you think about CT, you can see that one wire is coming out in and the other one is going out like that, right? They are not straight, like directly coupled from the outside. The reason, if you look at the left figure, right, a toroid, your cable is going through a toroid, right? So inside that big column that you have that toroid, so that you don't need, let's say, earth terminal there, right? You can see that it's a one conductor. So the conductor comes in and then goes out in the other side, like here. Come in and then goes out, right? And also, why then do you need these sort of things? Mounting your big insulator. Yeah, why do you need it?
Insulation.
Yeah, so insulation, and then typically this voltage of this line is around, let's say, 66 kV if it is a sub-transmission system, or 132 kV or 220 kV. It's very, very high voltages. So to have that clearance between the ground and the live component, then you need this sort of insulation. Why these? Probably this is not related to CTs, but if you look at these insulators, most of the insulators, they are having these sort of strange shape, right? It's sort of a corrugated shape, but then what could be the reason for having these sort of shapes? See, instead you can have one column like that, right? Why do you want to have this? It's expensive to produce it, right?
Generally, you can say that. Generally, we represent like one string is like for 11 kV. We do that, and if it is same like the curve surface area, the arc can't. I mean, there won't be in proper direction for that. It will be like there will be distraction with that. The voltage level side needs some fault voltage.
So there are, yes, that's correct. And then it's little bit with the technical terms, we can call that creepage distance. We call it as, let's say, the current flowing through this surface is called as the creepage current. So that we call that distance from live to the, let's say, ground along the surface is called as creepage distance. Now, if you have this strange shape, then you increase that distance, right? If it is a straight, it is very low distance. So while by increasing that, you increase the surface resistance because the distance is longer. So that's why that, otherwise that you may have to have this cylinder about 3 or 4 times higher, simple cylinder, right? Which is not practical. So that's why that they go with this. And the other thing is that these sheds, when it is, let's say, raining, right, it covers this underneath this certain part of it, right? And then that helps to keep the high insulation still. So that sort of different applications are there, but mainly it is the creepage distance. So, so in a CT, from practical perspective, what they do is they have this conductor going through this toroid, and in the secondary side there will be multiple turns. So in a current transformer, when you have large number of turns in the one side, in that side your current will be lower, right? Voltage will be high, but there is no voltage measurement here. It's only current measurements, because the flux produced in this core is based on this current. Therefore, what you measure in the secondary circuit is proportional to the current going through this conductor. So when you are dealing with these things like transformers or anything with the magnetic material or magnetic circuits, what could be one of the issues, main issues there? Say, why are we going to use this? To measure the current. So to measure the current, my secondary should show you some sort of a reflection of the primary current, right? Reflection of primary current appears in the secondary side. Can that happen always? When you have magnetic circuits, what is the assumption now? Pardon? Let's say this current in the primary conductor is proportional to the current in the secondary side. There is an assumption for that. What is the assumption? Why can we write that? Okay, how do you transfer that signal from primary side to the secondary? This will create a flux. That flux will create this current, right? So my assumption is that this current is proportional to the rate of change of flux here. The production of that flux is proportional to this one. Is it true always or not? Think about flux curves. Can you remember if you have done transformers?
The flux is constant.
Can you remember zone where the flux is not changing with current? What do you call it? You should know. I know, because you were he was doing the second year class, so I covered it. Can you remember the term called saturation?
Saturation current.
Yeah, saturation means that this core flux will not increase anymore for increase of current in this conductor, right? So if that happens, then how can this be proportional to this one? So that's why when you are dealing with these CTs, especially rather than VTs, yes, the problem is there, but it doesn't appear much in the VT's case. But in the CTs, when we are discussing about the CTs, there will be a separate section on saturation. How do you tackle that, right, in protection schemes, right? So I will explain those things when the time comes, but remember that is an issue, right? And that issue has been covered by the standards even, right? So I will discuss those interesting parts in coming weeks. This is the voltage transformer, right? So again, you can see those big columns, right? But the difference is that you have only one connection here, right? Because you just need this one voltage connection to the high voltage terminal. And the other side of the terminal could be grounded. That's why that you don't see it, right? So that the voltage is fed to this, right? And instead of now you have 3 columns instead of 2, because this one, the voltage is different level, right? In the previous one, it could be, 100, let's say 66 kV, and then here it could be 220 kV, right? I'm not sure the exact values, but it's like that. So now what it does, the voltage is fed to a small transformer here, and then the transformer secondary voltage is measured. That measurement is going through these columns to the substation control room, right? It's not measuring here, it goes to the substation control room, and then this measurement a voltage which is proportional to this voltage appears in the secondary side. So that is very simple. So that is how you do the measurements. Now, usually in real substations, you will see these columns one for each phase, right? So I will come to, if you are not familiar with three phases, some of you, I have included a couple of new slides just to give a brief introduction to three phase. So in a real power system, it's usually three phase, so that you will have one column for each phase. And if you look at here, it's only one wire is connected. So that's the easiest way that you could identify as, distinguish a VT from a CT, right? In the CT, that you can see that there were the two wires, one coming in and then going out. But here, it's the same wire, right? And the voltage is tapped here. Anyone knows little bit extra information again, why there are these sort of circles here? See, everywhere you can see. Is it just to make it attractive? Or is there a technical reason for that? What do you think? But
someone said in the answer in chat, in Zoom.
Corona effect, someone in the text, in the chat, they mentioned like corona effect.
didn't get it. What is
So
it?
in the chat, in online student,
Oh yeah.
mentioned, like,
Oh, sorry.
corona.
Yeah. Correct, Richard. That's correct. So that, have you heard about something called Corona? No? That's not the beer. I know that you heard about it, but right. So the Corona is some sort of an event that happens like ionization because of the ionization of air. When you have the higher voltages, the air around it is ionized, could be ionized because of that higher voltage. But that happens when you have sharp corners, because sharp corners, usually all these charges trapped on sharp corners, right? If you have a, say, normal conductor, it has sharp corners, because there could be strands, there could be, the surface is not smooth, right? So that you will have some small sharp corners. So to avoid that sort of sharp corners, it is, you have to have some sort of a smooth surface here. And also, it has been, using different research that you identify what sort of shape of conductor you need to place there to have these, to avoid this ionization process. So that is how that they have come up with these sort of different shapes. You can see that this one has a little slightly different from the other one, right? So basically, it is sort of a design to avoid Corona. Okay, finally, in the protection scheme, now we know that we have brain to process. Now we get the information from the CTs and VTs. Okay, now you process, the brain processes that information. Now you need to take an action. So you send the signal to take the action. What is the action? If there is a fault in the system, someone has to disconnect that system from the rest of the grid. So you have to disconnect one section from the rest of the grid. How do you do that disconnection? You need some sort of a breaker, right? So I would also say, if you refer it to the sensors, brain, and then it could be our hand. Like as an example, if he is coming to hit me, right? So that I can see it, he's coming, brain process, probably I will punch it, right? So that I use my hand as the action. So it's something like that, right? Put it in that way. So that brain sends the signal to somewhere saying that you are in danger, take an action. So that action is basically the opening the breaker. And it isolates the fault, and in a protection scheme, this happens when the trip signal is received. But if you think about in a household, let's say circuits we are using in a general, let's say building purposes. Have you heard about something called miniature circuit breakers, MCBs? Right? They don't have that processing thing. They have the sense, they sense it, but the processing part is embedded into that circuit breaker. Right? It could be not a very complex thing, right? It's some sort of identifying, let's say, current magnitude, that's all. So that it's not complex. So it will identify it and then take the action by itself, right? But when it comes to a circuit breaker, real circuit breaker, large circuit breaker in a system, it cannot do the processing part. Processing part is done by the relay, because there you have to take a lot of other considerations. You will find that what happens to the other part of the network, what's going on, all these things. And the circuit breaker is there to take the action. And then it will receive some signals from the relay and then take the action. And then if you look at in the real world, there are various different type of circuit breakers. It evolved from, let's say, AR-based circuit breakers to SF6 ones, or vacuum circuit breakers, right? So you can see here in the next slide here, see the AR blast circuit breakers are not used these days. They are very, very set of, they produce a lot of sound waves, right? It's like hitting a bomb, right? So it's, if you live in that sort of suburb, then you will complain everything, right? But it's usually not happening every day. So, but whenever it happens, then it's huge sound. So that people tend to remove these things from the systems. And then I haven't seen anything around this sort of AR blast circuit breakers now. And then the second generation of it is oil-based circuit breakers, where you can see that one of the common things these two is that you have this sort of barrel here. Here you have a tank, right? Why do you need that sort of large space when you are doing this sort of circuit breaker? Why can't you just in the normal air open it? Arc. It produces a lot of arcs. And then you have to quench that arc. Quench means that you have to suppress that arc in a different way, right? So that you use different mechanisms for that. In an air blast circuit breaker, it's just air. So they blast the air blow the air into the arc, but it will be huge, because the air is not a good insulator or cooler. But when it comes to oil is a very good cooling mechanism, right? So it can quench that heat produced by that arc. So quench the arc, and then it can take the heat produced by the arc. And then indoor substations are mostly with SF6. SF6 is sulfur hexafluoride, which is a gas, very, very very good insulating gas. So you can produce circuit breakers within a sort of a building environment. Usually the substations are outside, but SF6 substations can be mounted inside a building, right? So that the size is smaller and safety is high, and then a lot of other advantages as well. Of course, there are things like vacuum circuit breakers, where inside the breaker it is a vacuum, right? There's no gas inside. So, but maintaining a vacuum is really hard, right? Because if there is a very slight leak, then the vacuum starts to become a non-vacuum area, or pressure in the vacuum is increased, right? So that there are disadvantages, but still the vacuum circuit breakers are quite significantly used in the systems. And the other thing is that when you learn these different circuits and then associated components, usually industries, or they refer to the circuit symbols, right? It's not given as this is a overcurrent relay. They instead, let's say instantaneous current. They will relay, they will put number 50, right? And then in this case, number 51 is time delay relay, right? And then 51N, which is the neutral connected relay, right? So that sort of symbols are there. 52 is the given code for a circuit breaker. So you will find all these things in many documentations, but for your reference, I put one document in the learning resources, reading materials, papers and reports. If you go there, you will find something called NC device numbers, ANSI device numbers. Yeah, so that if you want to refer something later, just download it and keep it for yourself. So that gives you some base sort of understanding. If you when you read a document, what is this number? Just refer it to that, right? So all these circuit diagrams, they are usually coming with those numbers. Okay, so this is our plan which we discussed. I'm just going into the review part quickly. Okay, so now to learn all those interesting parts, we need to understand how you can, let's say, set relay conditions. Then there are terminology, there are some theories used, right? When the industries are talking about it, still these theories are valid. They talk about it. They use those things, right? Information like phase settings and then overcurrent settings or differential current settings. In all these conditions, they use this fundamental analysis. So therefore, I am giving you some sort of information about fundamental concepts, right? If you haven't done those things before, just let me know. I will guide you to some documents which are also available in this course site. But I'm sure most of you have done these fundamental concepts, but some of you may have not done per unit and symmetrical components, right? So I will start with three-phase, right? So any power system is, large power system is coming with a three-phase supply. What is a three-phase supply? It's nothing else like, it's the same AC voltage, but you will have, instead of one sinusoidal voltage, you will have three sinusoidal voltages, which phase angle of which differs by let's say 1/3 of the cycle, which is 120 degrees. So what you can see here in this document here in the slide, what I mentioned is that you will have three voltages, right? So to have three voltages, you need three lines, right? Three conductors. So that's why that in a three-phase system, minimum you will have three conductors, right? So the voltage appears on these each and every conductor. The peak level is the same, peak is the same, but as well as their frequency is the same, right? If it is 50 Hertz or 60 Hertz, it has to be that frequency. But you can see that their phase angle, phase setting is 120 degrees apart from each other, or 1/3 of a cycle, right? So that's the difference between these three. Now, this is the time domain representation of those waves, but you can represent it in phasor as well, right? So this is, if this is one of the phases, then the other voltage is 120 degrees lagging, and the third voltage is another 120 degrees lagging of the second one. So that is how the three-phase system is formed. And usually the maximum number of wires that you will have is 4 in a three-phase system, because sometimes that neutral is also taken from the transformer to a certain point, so that you will have a 0 voltage on the neutral ideally, remember, okay? So that neutral voltage could change, but ideally we would prefer to have 0 voltage on this line, right? And also we call this sort of three-phase system as a balanced system. We call it as a balanced three-phase system. Why? If you add all these three as vectors, then it becomes 0. So in a balanced system, If you add all these vector components together, then it becomes 0. And if you write the voltages in terms of, let's say if I want to analyze this, then I can write this as change it to 10. Okay. U max cos omega t. So they have no phase angle difference. U max cos omega t minus 2 pi by 3. Yeah. Um cos omega t minus 4 pi by 3. Right? So this is the real, representation, time domain representation of these three-phase systems. But you can also write divide by square root 2 angle 0, divide by square root 2 minus 2 pi by 3. Why did I divide it by square root 2 here? Yeah, so here this is the peak. So always we work with, this one is RMS. Right? Remember this. When you usually write in the full time domain, the magnitude is given in peak, but in the phasor form, most of the time, what I discuss here is the RMS quantity. But when you are looking at things like, say, saturation, sometimes the peak is also important because its saturation happens at a real value, right? So that the real magnitude is important in that sort of scenarios. But RMS is physically, you don't see the RMS, right? It's just a calculated quantity. Physical quantities, physically how the voltage changes is like this, right? So that the real value is important in certain cases, but for the calculation purposes, we use the RMS. Okay. So then, someone could ask, why the three-phase is used? Now, it's easier to work with single phase. Why do you need three-phase? You can put 3 wire, 3 single-phase systems, and then get more power. Why do you need then three-phase? Any response from Zoom? Why do you need three-phase instead of single-phase? Yeah, you can get more power from single-phase as well. All right.
More power, but less resources used to get.
Yes. So that's the correct answer, right? So it's more power with less resources, or you can say that high power density than a single phase system. The power density is high. Because in a single phase, if you want to get the same power, you need, let's say, 2 wires in one single phase. Which means that you need, for three single phases, then you need 6 wires. Right? But for 3 phase, you need 3 wires and maximum 4 if you have the neutral. So that here, maximum 4 wires. Same size. Right? I'm talking about the size of the wires are the same. And then in 3 phase, you don't need a large neutral conductor as well. Because usually the current in the neutral conductor is smaller, so that you can have a smaller conductor there. So because of those power densities, right, and then it's economical, and then small neutral conductor, because of these reasons, that 3 phase is quite interesting. Not only this, there is another technical thing which I didn't write here. Have you heard about 3-phase induction motors? So to work induction motor, you need 3 phase. Okay, so 3-phase induction motors, you need 3 phase there, because 3 phases can produce a rotating magnetic field by itself. Right, so it can produce a rotating magnetic field. If you apply it to a certain set of windings, then it can produce a rotating magnetic field, which is quite interesting for mechanical purposes, right? So that is another reason. Okay, So when it comes to three-phase, another important thing is that three-phase wires, which means that 3 wires, how can we connect these 3 wires? There are 2 ways, delta and then Y. These are the, pardon? Yeah, this is Y O star. Oops, what happened here? Sure, what happened? Pressed something and then that.
Sometimes.
Huh?
Subtitles are not like.
Uh-huh. How do you do that?
Maybe under more, you change it back.
Pardon?
Maybe if you go to down more, you can maybe change it back.
More here. Probably it's a part of the this one. I will end the slideshow and then restart it. Probably it's coming from the slideshow because I pressed something, some weird combination on the keyboard.
Controllers.
Pardon?
Controllers.
Nah, that is just a okay. Slideshow. Keep. Good. Oh, back. Easiest way. Just because otherwise, click on it. Okay. Sorry for that. Or someone asked a question. Yeah. So someone said that don't need a return wire for. I think this is for the 3-phase system. Yes, if it is balanced. Yes. Right. The balanced system is you don't need a return wire, but most of the cases it is not balanced. So that's why that they put a neutral wire, but then that neutral wire is, you don't have to have the same size as the phase wires. Okay, so this is Y or star. Right? And then this is delta. So these are the only 2 ways that the 3-phase system can be connected. And then in a Y system, that you have a neutral connection, neutral point, and then you can have a neutral wire connected to this.
Stephen, I think on our screen you've got the chat open.
Oh, sorry. Thanks for that. Neutral wire. Right? So, but in the delta system, of course, hypothetical neutral is here. Right? There's a neutral point, but you don't have access to that point. Okay? So, both systems are used, and depending on these configurations, your protection systems will be different. Right? So, that is very important. Depending on this configuration, certain number of harmonics doesn't appear in some systems, certain number of harmonics appear in the other systems. So that those are differences in the operation point of view as well, but because of the properties, they used in different environments. Okay, so that is what you need to understand. Both of them appears. Now, when you have that sort of connections, we need to define some parameters for this sort of 3-phase system. That's what we are going to use throughout the course. Let's say if you define A, B, C here, and let's say the voltage appear on this, let's say this is that's 0 point. Voltage here, we call it VA, VB, and then VC. Right? So VA VB and VC, they are called as phase voltages. Right? Remember that? They are, with respect to neutral, they are phase voltages. Now also that you can calculate VAB or VBC and VCA. Right? You can calculate them as well between the lines. Therefore, VAB, VBC, this is one I really don't like. Yeah. Called as line voltages. Right. Now, not only that, there is a relationship between these two quantities. So to develop that relationship, usually what you do, you know this is VA, VB, VC. And then if you want to find VAB, it is like this. Right? So VAB is this vector. So if you are writing the quantities, you can prove that VAB is equal to the angle between them is 30 degrees, right? Therefore, VAB is equal to VA. Do you agree with me? So the VA is the phase voltage, VAB is the line voltage. So the line voltage is 30 degrees lead in the phase voltage there. Or you can write in common terms, we can write V line is equal to V phase. Oh, sorry. There's a magnitude difference between them. Okay. So you can see that VAB is, the magnitude of VAB is different from VA, right? And then mathematically you can prove that the magnitude of VB is by considering those the triangles, you can easily prove that it is equal to square root 3 times VA, right? With the 30 degrees phase shift. So what this is square root 3 is very, very important.
So you saying V line?
V line is square root 3 times V phase, right? Oh no, this one has to be changed. Right? So that is something that you need to remember. And also, if you look at the currents, right? The currents in this particular case, the line and phase currents are equal because the same current is going through this phase. IA is going through this phase here, right? So this current IA is equal to this. Therefore, for a star connected or Y connected system, the line current is equal to the phase current. That is something that you need to remember. But if I am looking at, let's say, this system here, to be careful the directions wise. So this is VA, and okay, VAB is this one. So this is B, and this is C. right? The line currents for this system and the other second system, the delta and Y system, they are the same, right? They are the lines that are what you can see. Let's say when you go outside that you will see 3 lines. You don't know what's the connection in the other end, right? So therefore these currents magnitudes are the same on the lines. Therefore the line currents are the same. But for delta system, similarly, line current is equal to square root 3 times phase current magnitude. Put it in that way, right? So that is also quite important to understand, because sometimes in a 3-phase system, the secondary side CTs are also connected in delta and Y connections. So when you do the calculations, you need to consider these settings, right? What is the relationship between line and phase quantities? If you connect it in delta, it is this. If you connect it in Y, the configuration is this, right? So it's important to remind these 3-phase connections and then relationship between the phase and line quantities, right? I will leave it here for you. Find phase relationship. How do you do that? Right? Consider for the delta case and then find out what is the relationship between the phase current and the line currents for the delta. Like we already developed it for line voltages and phase voltages here by taking this triangle, right? And then I said that this one is leading by 30 degrees because VAB is leading VA by 30 degrees. Similarly, you can draw it for this one. This is the line current. These are the phase currents, right? So do it for this one too, or you can prove that line magnitude is square root 3I phase magnitude. Also, you can find the phase relationship between this current and this current. Okay? It should be 30 degrees, right? Find out whether it is leading or lagging. You draw it and then try to find it. Okay? It's the same thing, just for you to think about it, right? The relationship between the phase and then line currents. Okay? So I will, when I upload, I will write it here, but then I would like you to think about it, so that when you do it by yourself, sometimes you will come across with a lot of questions. So that is the idea. Okay. Now, another important thing with the 3-phase connections, this is not only 3-phase, but delta impedances and Y impedance configuration, right? Sometimes when you have connections in this form, which is in the delta form, you may have to reconfigure it to the Y form, right? Or sometimes if it is given in Y form, then you may have to reconfigure or reconsider it in delta form. So there should be some sort of a relationship between these two. So that relationship is given here, but we can even prove it. I will show it to you only for one, right? So that we can save the time. How do we find out what is the, let's say, relationship between these two different circuits? So if you want to find from externally, right, as an person who is looking at the circuits externally, the total impedance between 2 points should be the same, because I will have wires like that. Right? So externally, what I will do, between A and B, I am looking at between A and B. Right? And then I'm looking at the same A and B from here. Right? So if you're looking at the same thing, two wires, you should see the same thing. So the impedance between these two A and B in both circuits should be the same. So if you look at, let's say, impedance between A and B, if you look at it, in this circuit, the delta circuit between A and B is ZC parallel, or say ZC parallel with ZA and ZB. Do you agree with me? Between A and B, right? The impedance between those two is ZZ parallel with ZA and AB, right? Yeah, AB. So ZA plus ZB. Do you agree with me? So that is the impedance that you can see from A and B. Forget about the C1. Right? And then if you look at the same thing in the other one, between A and B, there is no connection no contribution from Z, because that line is now immaterial for the impedance between A and B. So the A and B, the impedance is ZA plus ZB. Oops, sorry. This is Z1 plus Z2. I should wear my glasses. So, do you agree with me? So, once you apply the same thing, right? So now you can very easily calculate a relationship between ZA, ZB, ZC and Z1 plus Z2, right? Similarly, you can look at between B and C and C and A. Got it? So how many equations you will have? 3 equations, and then you have to solve for 3 unknowns. So that is, you don't have to prove these things in the exam or anywhere, but you need to know how one get to the solution, right? So the relationship between these 2 circuits are defined, or to calculate the relationship between these 2 circuits is formed using these 3 set of equations, right? So that you can calculate, let's say if these 3 impedances are given, then you can calculate the Z1 using this equation. So it's easier to remember, because ZB, ZC means that, say, ZB and ZC, which are basically let's say when you take Z1, it is connected to A. So the 2 impedances are connected to A, that is ZC and ZB. So you multiply those 2, divide by the addition of them. If you take Z2 is connected to B, it is connected to B, multiply these 2, ZA, ZC, divide by the addition of them, likewise. Right? So it's easier to remember, but this is how one can, yeah, right? So, any questions so far? Yeah?
With the impedance, they're all the same, right? In this course's context, because it's balanced. So
Sometimes that you can have unbalanced ones. So if that is sort of, they are not equal, then still you will have the equivalent y, but then they are also not equal, right? So that's Yes, in most of the cases we are talking about balanced systems. If it is a balanced system, then you can prove that what is the relationship between this one and this one there. Say if, is it same?
By 3.
So, in balanced system, very good question. In balanced, so Z1 is equal to, you can see that multiplication of this becomes squared, right? Therefore, ZA divided by 3. Or you can write ZA is equal to 3 times Z1. Both are correct, right? So that is the relationship between these impedances for a balanced system. Okay. So I will do a calculation related to this on Friday class, right? Because I assigned that class for these sort of calculations. I will give you time to go through these review problems, and then on Friday we can discuss those questions. Okay. So these are not 100% related to the protection, but that knowledge is required for the protection system calculations. Then, this is another important thing. Some of you probably haven't done this part, but some of you have already done. In current voltage and power calculations for power systems, right, since the systems are complex, you know that the same voltage doesn't appear every part of the network. So if you go into distribution, probably as an example here, it's very clear in this one, you can see that this is 3.3 kV, this is 11 kV, and then probably when you go into these high voltage buzzers, it could be even 132 kV or 220 kV, right? So there are different voltage levels, right? And then the impedance of this network, let's say the impedance of the wires here, and then impedance of the wires here, they are very different. When you come into these high power circuits, the impedances are very low. But when it comes to the low voltage networks, the impedance might be higher. So that you are working in very large range of voltages, currents, and then impedances. When you have that sort of system, when they are not, say, in the let's say when they are in different levels, it's really hard to do the calculations, right? Because sometimes that you need to transfer the quantities that you calculated in this network to the other side of the transformer. So which means that you have to multiply by the voltage ratios or divide by the current ratios, right? So the complex calculations. So to avoid that, a method has been introduced called per unit approach, right? What per unit approach is done is that they use some sort of a base quantities to bring every quantity into some sort of a same level value. Like let's say everything is now marked based on 1, let's say around 1, right? So all values are around 1, voltage values, which means that you have introduced some sort of a base quantity and then you divide every voltage by that base quantity, right? So that you are now operating in some sort of a same range. So it's easier to do the calculations and easier, especially when you are dealing, let's say, working with simulation software. It's easier for the software to work it out, because one of the things when you are doing these calculations in different voltage levels and current levels, the error in one level could be different in the other level, because then you are working with the magnitudes, right? So let's say in the let's say in the lower level, voltage level, if it is 1000 amps, you can have, let's say, 1000 amps plus or minus 0.5, plus or minus 10 amps. All good, right? 1010 or 990. But when you come to another level where the maximum current, that 1000 amps reflects as, let's say, 50 amps. Now if you set the same scale there, 50 amps plus 10 is 60, minus 40. Now 40 to 60, it's meaningless. Error is large. So that's why that it's better if you are working in the same scales. So to achieve that, we introduce something called per unit approach, right? So in the per unit approach, the advantage, as I said before here, typical single line diagram is the one that's shown at the top, right? So we have generators, transformers, see? And then when you do the calculations, you do certain calculations in this here, and then transfer it across the transformer, do the calculations here, something like that. But when it comes to a single line diagram, this whole thing can be represented as a one single line. So that we, here in the first one, the two circuits in both two sides of the transformers are independent. There's no link between them. You do the calculations in one side and then bring to the other side. But when it comes to the single line diagram, it's a one circuit like that. So it's very easy to do the calculations. But that is only for calculations. So when you come to the, I didn't give you a break, right? You should have asked. Do you guys need a break? Oh, I can continue until 9:45 and then we'll have a question session or something. Yeah. Anyway, so that it's the per unit approach where you can combine every impedances into a one single line. Okay. What is it? How we do that? The next question is that yes, we want to convert it to a one single line. So the approach is that you need to specify something called apparent power for the whole system. Let's say certain value, 100 MVA is my apparent power in this whole system. So that is defined. You define the base power for the whole system. And the second thing is that you need to define the voltages. That voltage definition, I will come to that when we are doing the calculations and then a little bit later, how we do define those voltage. There is a certain criteria for that, right? How we define the base voltage, there is a certain criteria. That criteria we will discuss. But now at this stage, remember, we need to define the apparent power. We need to define what is the base voltage. So two different base quantities. So base quantities means that the real quantities will be divided by the base quantities. Right? So as an example here, transmission line operating at 132 kV and 100 MVA power, we can say that, okay, my base voltage is 132 kV and the base power is 100 MVA. Right? So typically those quantities are defined according to the ratings, right, of the lines or system. So that's why as an example here, you can say 100 MVA base power, 132 kV voltage. And why we only define these two? Because you don't have to define other two, because there's a relationship between current, voltage and power. So once you define S, we know that V times I is equal to S, therefore S base defined by V base will give you I base, right? And then the impedance is voltage divided by current. Impedance is equal to voltage divided by current. Therefore, voltage base divided by I base is giving you Z base, or you can rewrite it in a way V squared divided by S. So, once you define S base and V base, all the other base quantities are already set. So how do we calculate the per unit quantities? The given quantities will be divided by the base quantities. So that's what we are going to do. So all given quantities, let's say, remember, if the power is given to real power plus reactive power, probably you learned something called reactive power somewhere in previous courses, right? All the real power is the real active power which does the work. reactive power is the power which is, how do you define reactive power? Which is not doing the work. Active power is the power which really does the work. What is reactive power then? Not doing the work, or what is the impression that you have? Can someone tell me in the chat as well? Like, how do you feel when I say reactive power?
When you transmit a high voltage on the transmission line, you need some reactive powers to.
These all I agree, 100% agree. Okay, but what I want is that what is it? You need to have some, when you have active power, you know that. What is power? It's something which is doing the work, right? Like, let's say if I want to move this one here, and I need power, right? And then we know that if the motor is rotating, that is, and then doing some work, that is active power. If there is a heating element, right, generates heat, active power, right? So it's doing something. How do you feel reactive power? Someone wrote something here? No.
It's like when it induces like magnetic stuff. No.
Yeah. What do you feel like when someone says reactive power?
Is it what? Could you look at it in a way where reactive power is what brings real power to the location? Not really. No, you can't look at it that way.
Real power? No, it helps.
Yeah.
It helps. But then, what is it really? Yeah, tell me. Whatever you feel. Yeah?
Support the real power.
Yeah. Actually, it's a power, yeah, that's true.
How different types of loads affect, like you have capacitive loads, inductive loads.
Oh, yeah, now you're coming there.
If you've got inductive loads, then you have positive reactive power.
Yeah, that's all these things, yes, correct.
Yeah.
I think you know it. But how do you feel it? Like, what is it? That when I ask real power, then you can explain it, right? Like, you know that this is the thing that it does the work.
Real power is actual work.
Yeah.
Reactive power is everything else that goes on.
Everything else means that everything.
The waste that you don't see.
It's not a waste.
The work that you don't see.
The work that you don't see, which means that there is a real work. Is there a real work associated with that? Or?
Yeah, because you get inductive loads like when stuff is spinning, like.
Yeah.
So you get, if you have a motor, like it spins the actual work, but
It's like the fuel to spinning. So I think the reactive power
Doesn't have to be always spinning,
it's like
because
we have an analogy, right? I will compare with one. If you pour a beer in a glass, so beer will be like saying the real foam about is like the reactive power, like the compensating power, like to the loads.
I can see that you know it, but I think the fundamentally, what is it? I think you know where it's to, what it does. Like, what you said is correct, right? The transmission, the related to transmission, what you said is correct. But yeah, someone is there. I want to hear from you. Yes, see, here also someone said that yes, that is correct. Reactive power regulates voltage. That is correct. But then what is it?
To keep the power stable.
Pardon?
To keep the power stable.
Yes, like that's something that does this. But what is that something? Right? That's my question. It's easy. That is the power stored in an inductor or capacitor. That's all. Okay? Reactive power is the real power which is stored in a reactive element. Isn't it? Like, what is the power, the maximum? That is the maximum that when it comes to the power system, that's the maximum, peak of it. You define it as reactive power. That is the maximum power a reactive element can released or absorbed. So that you define it as reactive power. And then what you said, it's absolutely correct, right? It's related to the magnetic field, it's related to, transmission and everything, right? But that is the element that when you look at it physically what it is actually the maximum amount of real power that can be stored in or supplied by a reactive element.
So then inductors, they absorb reactive power.
That's coming from the definitions, right? So that absorb and the supply, that is, we made some sort of rules to understand it. That's all. Probably you heard it, because when I taught circuits, can you remember I said something called passive reference configuration? That is the first part of circuit learning, passive reference configuration, where that you mark a special directions, like when you mark the voltage, like this, right? Then we mark the current like that, something like that. So there's a passive reference configuration. When you define things in that, when the P is positive, we call it as a load. When the P is negative, we call it as source, right? Similarly, when the Q is positive, we call it as reactive power absorb. When the Q is negative, we call it as reactive power supply. So that is how those definition comes. Now we forget about all those things. We quickly mention that the inductor supplies reactance. That's the norm that we set. That comes because that is easier for analysis now. But that comes from that the power stored or supplied by a reactive element, right? So, right? Think about those things when you have time. Oh, what is that? These guys are always talking about it. What is it?
So they're
right?
both technically storing it, but in terms of like
In one cycle, both of them stored. Another cycle, they supply.
But for like
Both of them supply and store.
But for circuit analysis convention, it's easy to just think about one and solve it once.
Exactly. Because we are in the circuit analysis in AC circuits, you are working with the RMS and then all those quantities. We are not looking at the cycles, right? So in one cycle, inductor stores, and the other cycle, inductor supplies. Capacitor, one cycle it is stored, in the other cycle it is supplied. And then those cycles are not overlapping, right? So that's why they have negative relationship, right? So, yeah, so that's why the Q, all these things comes here, okay? So, when you have the power, as I said, for your calculation purposes, the reactive element marks with J, because those two are two independent things. P and Q are independent things, so that one way of mathematically representing them is that two different axes, X and Y. So, for the calculation purposes, you put the reactive with the imaginary component, right? So, P plus JQ. Oh. Thanks. Now, when you have that P plus JQ, still you have one S base. So that remind this. You don't have something called P base or Q base. Okay? So the S per unit is equal to P plus JQ divided by S base. P divided by S base, Q divided by, and then P per unit and JQ per unit. Most of the time you will use the per unit quantities in that form. And voltage per unit, we know that voltage, real voltage divided by the base voltage, current and voltage, the impedance, they are the same. So remember, base quantities, are they real numbers or complex numbers? Base quantities. Base quantities are only real numbers. Per unit quantities, they can be real and imaginary. Remember those small points, right? So the base, they are always real numbers. Even Z base here, you can take the magnitude as Z base, right? So in most of the cases, you can take it as a magnitude here. Okay, so this is a small question for you to think about it, how these base quantities can be calculated for a single phase system. So I'm say that's it. Yeah. Okay. So what I will do, I will go through the theory here and then do these calculations in the next class, but try to work it out before Friday by yourself, right? Come to the class and then we will discuss. It's just applying the theory which I described so far. And the other important thing is that per unit quantities for three-phase systems, right? What is the difference between three-phase and single-phase systems? And then how we are going to find base power and then base voltages. So for a three-phase system, base power is that if you have a single-phase system, 3 times that single-phase power is equal to the base power for a three-phase. Remember? And then base voltage is line-to-line voltage. In most all power engineering calculations for three-phase systems, we are dealing with line-to-line, right? And base line current is assumed to be equal to phase current. That's what we do. The reason one can ask that, why then in a delta system it is different, but we assume that the network is Y connected. Doesn't matter, right? Network is Y connected and then work it out. Base impedance is the same as per the per phase quantity. So base impedance is the same as per phase. So there's no difference. So if you write it here, again, remember total base power 3 times phase, line base voltage is equal to square root 3 times phase voltage, base current is equal to, remember, you can say that phase current is equal to total base, if you are taking the 3 phase, divide by square root 3 times PL base. Remember, this is line with this square root 3, right? Because for 3-phase systems, square root 3 VLIL is equal to S. Don't miss that square root 3 because that is one of the major mistakes most of the guys are doing in the exams, right? Found that probably sometimes 40% of the class, if there is an error is there. Square root 3 VLIL is equal to S. Remember that because it's a mistake that you do in an exam environment because of the stress. I think sometimes it's not that you don't know, right? You usually forget to put that square root 3. I've seen it many times, so remember that. And base impedance is again, if you are looking from the line quantities, VL squared divided by S total base. It's easy, right? Remember these relationships, then you can calculate the per unit quantities for this 3-phase system as well, and then compare it with the first one, right? And the other important thing is that how do we select when you have, or let's say when you have different base operating conditions. Sometimes, let's say you have a transformer which is 10 MVA, but your system base you selected as 100 MVA. Now you need to change the, let's say, impedances of one system to another base. So there is some sort of base formula is required to change the impedances from one setting to another one, right? So that's I'm going to discuss with some questions in the next class. Before doing that, that conversion comes from this one, right? But then that is the relationship between per unit quantities for one system to another system. Let's say as an example, impedance is given for 132 kV 10 MVA system. How can I change it to a 132 kV, let's say 100 MVA system, right? Because at the end of the day, you have to change it to a constant power base. So I will give you some examples on on Friday, so that try to go through these slides, and then I will work out those examples so that you will understand why I have to do those changes. Okay? So these are the equations for that. Probably you don't have to remember them. In some of the exams, sometimes you may use them, right? If it is required, I will try to provide it. Can't remember whether I provide this equation or not, but if it is required, then I can put it into the exam, the equation list. But remember that I'm going to use these in the next coming Friday. And another, in the per unit calculations, another important concept is that selection of the base voltage for transformers. How do you select the base voltage for when there is a transformer in the system, right? Always you select it in a way that the base voltage is equal to the voltage rating at that side of the winding. That's all what you need to know, right? But it's not always the rating of the winding if you are using a different tap setting. Have you heard about tap setting of a transformer? Let's say transformers can work from, let's say one transformer is primary 11 kV, secondary side you can change from 129 kV to 132 kV, say, some settings, right? So if you are using a different tap setting, you have to use that base voltage correspond to that tap setting, not the 11 kV to 132 kV. So if you are using 129 kV, then your primary is 11 kV, the secondary base has to be 129, not 132, right? So because I will explain why you need to use it. Do I have time? Yeah, it's you can prove it. The reason is that, can you remember that when I drew that per unit diagram, I drew it in a way that a single line, like all the impedances are connected. So for a particular transformer, if you are looking at from the primary side, and then if you are looking at from the secondary side, should you see the impedance as the same value or not? If you are looking at, let's say, this is my single line diagram, right? This is the generator, and then generator is represented like that, and this is my transformer, this is wires, this is transformer, right? Now, if I am looking at the transformer impedance from this side, and then if I am looking at the transformer from this side, what is the impedance of the transformer? This is the impedance, is a transformer. So if I am looking at from ZTF from the low voltage side, should be equal to ZTF HV. This is per unit, okay? From both sides, it has to be the same impedance. You can only get that if you strict into the criteria where the base value from the primary side and then the base value from the secondary side are equal to those winding terminal ratios. So like, let's say if this side is 11 kV, the other side is 132 kV. you can get the same impedance only by selecting those voltages like that. So that's why when you are jumping across the transformers, you have to select it in that specific way, right?
So you're saying if you use a tap change and go from 11 to 129, you have to use 129?
Not the primary side is 11.
Mm-hmm.
Secondary side can change slightly from 129 to let's say 133.
Yeah.
So if you are using 129.5 tap change, right, then you have to use that corresponding voltage in the secondary side as the base.
Yeah.
Okay, so if you don't use that, then that impedance will not be equal from both sides when you are looking at it, right?
Yeah.
So that because it comes with the turns ratio, we can prove it, right? I have the proof in the next page, right? If you maintain the turns ratio is equal to the voltage ratios you use, then only the impedance looking from the primary side and secondary side will be equal, right? So, but we need to make it equal because you put everything in one line, right? So that is the reason. Yeah. So I think I have put this explanation here as well, right? Okay. So the next important part is I have a couple of review questions for Friday, and any questions so far? 9:42. I can start some discussions before going into this proof. Any questions so far? Anything related to the course? No? Okay. So if you look at this transformer, what I am going to prove is that, right, to make the impedance equal from the primary side or secondary side, I need to use the voltage which is relevant to this Vx and Vi. They are the terminal voltages as the base quantities. If you don't use them as the base quantity, they are not equal. So that's what I am going to prove, right? So if you are looking at Zxb, that is the base from the primary side, which is Vx squared divided by S, right? If you select Vx, right, as the base quantity in the primary voltage, and then the S is the total power associated with this circuit. From the secondary side, Zy base is equal to Vy squared Zb. Sorry, S. Now, we also know that using the impedance transfer across the transformer, secondary side impedance, any impedance from the secondary side multiplied by Nx divided by Nay squared is equal to the primary side. That is the transformer impedance transfer. Now, this will be equal to Vx divided by Vy squared times Zy. Why? Now the turns ratio is equal to the voltage ratios. Now Zx per unit is equal to Zx divide by ZXB. Right? So ZX is the impedance from the secondary side, divide by the base impedance. That is the per unit impedance from the X side or primary side. We replace it here, Vx divided by Vi squared times Zy divided by Vx squared times S. Got it? So I just replace Zx with Zy times Nx divided by Ny. Instead of Nx divided by Ny, I wrote Vx divided by Vi squared. Zxb is, since it is divided by Zxb, I replace S divided by Vx squared. So that is equal to, if you simplify it, you can rewrite it Zy divided by Vy squared S. Right? It is the simplification. Vx squared is cancelled out. Right? Now, this is equal to Zy divided by, what is Vy squared divided by S? That is Zyv. So the base quantity from the y side. So Zy divided by Zyb, what is that? Impedance in the y side divided by the base quantity in the y side. We call it as Zy per unit. Now can you see that Zx per unit is equal to Zy per unit? Why it is equal? Because when you define the base quantities, you used the transformer voltages are equal to the turns ratios. That is the point there. Right? If you didn't use it, then those Nx divided by Ny is not equals to Vx divided by Vi. So always, therefore, turns ratio has to be equal to the voltage ratio. That comes only when you refer it to the corresponding correct voltages. Right? So when you are doing, what are you doing with the tap settings? You are changing the turns ratios. So you need to consider that change when you apply it to find the base quantity. So remember those things because there are some questions based on that. Okay. So these examples I will cover, and the next section is actually the main section is on symmetrical component, which I will cover in the next day. And also this is also in the last minute something for you to think. When you are dealing with the transformers, sometimes the polarity is very important. Not sometimes, most of the time. Right? How do you define why the polarity is important, first of all? Yeah, but if you are not looking at the polarity, what is the change or the difference between the two different voltages or currents? If you are not thinking about the polarity, is there a difference between them, or they are like if you are not looking at or considering, if you are not considering the polarity, right? What could be the, let's say, difference between those two?
The load is actually supplying to the source.
Yeah, forget about that load and source. Just focus on transformer.
Okay.
You have the primary voltage and the secondary
Then
voltage.
you think it's stepping up when it's actually stepping down.
Yeah, what is the correct terminology we use? What you said is correct. How do you express it in technical terms? Not stepping up, down. What is the difference between those two voltages then?
Higher or lower. So you confuse the LV side with the HV side?
No, because that's the voltage, like 11 kV to 132 kV, right? It is the difference between the phase. what you said is 180 degrees phase shift. When something goes up, the other goes down. Right? So that 180 degrees phase shift can be considered if you are closely looking at the dot. Right? Towards the dot direction, the voltage has the same phase. That's what it says. So if you take, let's say, 2 transformers in the system and then connect one transformer in one direction, the other one in the other direction, then voltage in one transformer goes up, in the other one voltage goes down. So there will be a blackouts after that, right? Because both transformers will be damaged. So it's very, very important when you are dealing with the transformers looking at the polarity. Okay, so I will stop there, and if you have any questions you can ask now, or I will come on Friday at 2 o'clock and then we'll start to do some calculations, and then we'll do the tutorial which is based on per unit calculations. Okay? Any questions from Zoom? No. Okay. Thanks, guys. Hello. Is there a difference? Yeah. Okay. Not the resistance. Can't remember. I'll look at it. Can you please send it to me? Yeah. Thanks for that. Okay. So, any other questions? No. No. I'll have to set the meeting. Gary said that he can meet on Friday. I'll set that on Friday. I didn't do anything. I know that you were busy in the last week, so I just took the like. So if I set the meeting, it's not good for you. Okay. Yeah. When do we have the 2:30? I think I have a meeting with Professor Zahar.
I'm here the whole. I can do anything. Can do it now. I'm not really prepared for it now. I was gonna. What do you want? Oh, so pretty much during the week, all I did really was just gather as much resources as I can for research and just like everything I.
We'll have a quick meeting.
Okay.
Right?
Yeah.
Not now, but we'll go.
Okay.
On the day, we can have a meeting.
Okay. So pretty much I just gathered everything I have. So I know Lagat sent me a bunch of like circuit breaker courses that also have like point and wave stuff in it, like relay stuff. Mm-hmm. And then David Peter, he's done like a lot of presentations about it. I just gathered all of that because I'm assuming I'll have to write background theory.
Yeah. See, your progress report is due in week 5 or something, right?
Yeah.
So by that time, what you need to do is, see, first you look at the marking scheme, you know that thing, and then because what happens is that if you don't look at it, if you miss certain sections, you can't give it.
Yeah,
Right.
Yeah.
So to avoid that, the best is you go through that marking rubric.
Yep.
Right. And yeah, I think I have to.
Something I noticed was